Hi, my name is Morten, and today I'd like to talk about OTAcast, which is a solution we built here at Steinwurf for doing efficient file multicasting using perpetual erasure codes. And in this talk, I'm gonna dive a little bit into the algorithm, the perpetual algorithm that we use in OTAcast in order to give you a glimpse of how OTAcast works behind the scenes. First, a few words on Steinwurf. So we were founded in 2011. We're located in Aalborg, Denmark, and we do software development and software licensing of high-performance erasure correcting codes, also known as ECCs or FECs. And this includes both traditional block codes, but also next-generation network codes. So FECs, ECCs, ALFEC, there are many acronyms to describe the erasure correcting code. And this can be a little bit confusing because there are other very related algorithms that use similar acronyms, but I'll get into that a little bit later. So erasure correcting codes is actually a quite old technology, but in the past decade or so we've seen quite a number of technological breakthroughs, both in the algorithm design, but also in the way that we use these algorithms in systems. And we believe that they will become a key enabler for building both low latency applications over the internet, but also for what we are going to be talking about today with OTAcast, how we can build very, very efficient and scalable multicasting and broadcasting systems. So let's take a look at the use case for OTAcast. So what we want to do is that we want to transmit reliably a file, could be a small file or large file, to a group of receivers as efficiently as possible. And if you look here on the right, you can see the communication scenario. We have a sender in the middle. We could also have multiple senders, and then we have devices that are moving in and out of range. And we would really like to build a system where we don't need to have any feedback from the senders, from the receivers going back to the sender, because this would take time and it might even be difficult to manage. We could have many receivers within range at a given point in time, so this would quickly become unmanageable. So we would like to build a stateless solution where the sender can just transmit data and the receivers are just collecting data. And if we want to do this, there's at least two questions that we need to answer. And the first one is, how can we transmit useful data if we don't know what previously has been received? And the second question is, how do we transmit useful data when multiple receivers are within range and they're missing different pieces? So if you think over how to solve or how to answer these two questions with conventional technology, you will quickly discover that this is very, very difficult. But it turns out that there is actually a very simple and efficient solution to this, and that is to use an erasure correcting code. So before we dive into the algorithm that we're using in OTAcast, it might be worthwhile to spend a little bit of time on some background material just to give you an idea of how an erasure correcting code relates to other algorithms in use in communication systems today. So if you have a background in communication networks or telecommunication, you're probably very familiar with the first two types of algorithms that I'm going to talk about. The first one is called an error detecting algorithm. And error detecting algorithms work across a single data packet. And what they do is that they calculate some redundancy bits. And these bits are typically appended to the packet during transmission, and then a receiver can use these bits to actually see whether or not any bit errors occurred during transmission, or if the packet is somehow corrupted. If it's corrupted, then the receiver can throw away that packet and we will have a packet loss. In order to mitigate this, there is another very widely used type of algorithm that we can use, and that is called an error correcting algorithm. And this is where some of the acronym confusion comes in, because many times this type of algorithm is also called an FEC, for forward error correcting algorithm, which is also what we're using here. For the remainder of the talk, if I say FEC, I'm going to be talking about a forward erasure correcting algorithm, but for this particular picture here, we mean forward error correcting algorithm. And the forward error correcting algorithm works also across a single data packet, and we use the algorithm again to calculate some redundancy bits that are appended to the packet for transmission. And then at a receiver, we can use these bits not to detect any errors, but actually to correct some of the bit errors that occurred during transmission. If too many errors occurred, we still have the error detecting algorithm to figure out whether or not the packet is corrupt. And if it is, we will still have to throw away that data packet, and we will still have a packet loss. And it turns out that we actually have a third type of algorithm to deal exactly with this problem, namely the problem of packet loss. And that is called an erasure correcting algorithm. Erasure correcting algorithms are not in very widespread use in communication systems today, so you may not be too familiar with them. So let me try to explain a little bit how they work. So instead of working across a single data packet, erasure correcting algorithms work across multiple data packets in order to deal with the problem of packet loss. So on the right here we have a small example that shows how we can use a simple erasure correcting algorithm to deal with one packet loss. And we have here two data packets, packet 1 and packet 2, and each of them consists of 4 bits. And we want to create an equation that describes both of these data packets using our erasure correcting algorithm, such that if we get 2 out of the 3 packets, we can still recover the original 2. And in this particular case, it's very simple. We can simply compute the sum of the 2 data packets by taking the XOR of the bits of the packets. And here I call that packet sigma. And already now we have this very interesting property that if I receive 2 out of the 3, if I receive packet 1 and packet sigma, I can recover packet 2, or if I receive packet 2 and packet sigma, I can recover packet 1. And we sometimes call this a 3,2 code because we're sending 3 packets and any 2 out of the 3 will allow us to recover the original 2. And this is really a really powerful technique for dealing with packet loss. And using some more sophisticated mathematics, we can actually do approximately any n, k code to match the size of our input to the packet loss that we are expecting to observe on the network. So if we look at this concept of creating equations, that is really at the heart of all erasure correcting algorithms. So let's generalize that a little bit and see how we do it from a more general perspective. So introducing a little bit of coding terminology here, we now have our data packets and we call them our source symbols. And these are arranged in a matrix, in this case called M. And then when we want to create an equation, we just pick a set of coefficients here and multiply that vector of coefficients onto our data matrix, and then we get a linear combination of our data symbols as an equation, as the output of that multiplication here. And this is really what all erasure correcting algorithms are fundamentally doing. There are different ways of picking these coefficients, and that has different consequences on how easy it is to both create and solve these systems of linear equations. So there's a couple of high-level observations that are relevant to make when we are talking about something like OTAcast and to explain the way OTAcast works. As you may be able to see from this picture here, the computational complexity of creating an equation here highly depends on how many non-zero coefficients I have in my encoding vector. Because if I have a lot of zeros, it means that my output equation over here is only a linear combination of very few of the source symbols here. So this makes the more zeros I have, the more computationally light my system becomes. And we also call this a sparse system sometimes, because sparse means we have a lot of zeros and only very few non-zero coefficients in the system. Another property is that we sometimes also can optimize the memory consumption if we have a lot of non-zeros a lot of zero coefficients. We don't actually need to store those, and so that can also be used to optimize the memory consumption of the algorithm. On the decoder side, what we are doing when we want to solve this system of linear equations, you can have many different decoding algorithms depending on the erasure correcting algorithm used, but in many cases we can simply decode using standard normal Gaussian elimination on the coefficients and the equations or the incoming equations, and as long as we collect enough of these equations, we will be able to solve this system of linear equations and get out our original input data. The way that we build OTAcast is that we are using a specific type of algorithm for picking these coefficients called RLNC, which stands for Random Linear Network Coding. And there are two key properties that we are going to be using in OTAcast that comes from RLNC, which is that in RLNC we pick these coefficients entirely at random, and that has two consequences. One is that I can have as many input symbols as I want here. So if my file is my input, I can have any size file as input here, because I can always create more coefficients that are just picked at random. The second property is, because we would like our OTAcast solution to support this stateless behavior where we can just keep on transmitting equations until everybody is done, we can also always pick a new random vector up here, right? So we can create as many of these output equations as we want, because if we want to create a new equation, we just pick a new random encoding vector, multiply it onto our data, and then we get a new equation. So the sender can just keep on transmitting until we're basically done. So these two properties are important for OTAcast and are one of the reasons why we built OTAcast on top of an RLNC algorithm. So let's also take a look at why it is that the erasure correcting algorithms solve the two questions that we introduced in the use case description. So the first question was, how can we transmit useful data if we don't know what previously was received or has been received? And this figure tries to illustrate that. So in here we have 4 original input packets that we want to transmit, and the way that we do that is by passing them through an encoder, which is the one that implements our erasure correcting algorithm, and this encoder will just start producing these output equations, and these equations describe the original input data and are then sent over a lossy network where some of them will be erased, or we will have some packet loss on that network. On the receiver side, all we have to do is that we have to collect these incoming equations, and as soon as we have enough as many equations as we have unknowns, we can pass them to the decoder, and the decoder will be able to solve this system of linear equations and get out the original input data. And so this means that we can transmit data even if we don't know which packets are going to be lost. We don't have to care about the identity of any particular packet. All we do is that we just create more and more equations, as many as we need in order to overcome the packet loss on the network, but we don't need to know which equations has previously been received or what is the state of the decoder. We just need to keep on transmitting until it has enough, basically. So this solves this first question that we had: how can we transmit data if we don't know what previously has been received? So in order to answer the second question, I've tried to illustrate that on this slide. So first, let's take a look first here at how a traditional uncoded system solves this problem of receivers missing different pieces. So here I have a source which has 4 packets to transmit, and then I have 4 receivers to receive this data. And in an uncoded system, I have to pick one of these packets. I can only transmit one of these packets at a time, and this means that if I pick packet 1, it's only going to be useful at user 1 here. If I pick packet 2, it's only useful at user 2, and packet 3 is only useful at user 3, and so forth. And this means that in order to fix this unlucky situation here with 4 packet losses, I need to retransmit all 4 packets once more. However, in the coded system, because I can generate one of these equations out of my original input data here, I can transmit this equation, and then this equation will be received by all of these 4 receivers here, and they can simply solve for the unknown that they are missing. So this means that with a single coded transmission or a single equation, I can fix all of the packet loss and all of the receivers at the same time. And we sometimes call this the multicasting gain. And this is one of the key features of using an erasure correcting code in these types of systems. So if we want to understand a little bit better what is then the performance gain that we're going to be seeing using an erasure correcting algorithm, we ran some basic simulations in order to try to illustrate that. So important to say first here, in these simulations here, we are using feedback in the system because we do need to know which packets were lost in order to operate the uncoded solution. Otherwise, it would perform. It would be impossible to make it work basically. So in this box here, we use feedback in order to optimize the transmission. So the sender will know if somebody lost a specific packet. That is important to say up front. So we have 2 cases here. This is for 1% packet loss on the network, and the case over here is for 10% packet loss on the network. And then we have on the x-axis here, we have an increasing number of users or receivers. And then on the y-axis here, we have the average number of transmissions per packet in order to get it successfully delivered. And if we look first at the 1% network loss case here, then we have our uncoded solution. In this case, we're transmitting a packet. If somebody lost it, we need to retransmit it again. If somebody still are missing it, we need to retransmit it again, and so forth. So if we look, for example, at 100 receivers here, we see that at this point, we need to retransmit every packet twice, right? So we have 100% overhead here. There will always be somebody that needs this one retransmission again. We can improve this situation quite a bit by using a traditional FEC block code, in which case we have a block of 8 where we have 7 data packets on the yellow curve here, 7 data packets and 1 equation. And you see by doing that, sending this 1 equation for every 7 data packets, we already stabilize the system quite a bit. However, as the number of users increase, we see that when there is enough receivers in the system, there will always be somebody that lost more than this 1 equation, and we still need to do some retransmissions. We can improve this further improve this by looking at, for example, the green curve here, where we are taking 6 data packets and 2 equations. Now we see the system is almost 100% stable. We still have a little bit of fluctuations here when we reach 1,000 receivers. Because again, at this point, there might be one unlucky receiver that lost more than 2 packets from this block here. And if we want to fix this problem, we just have to increase the number of equations that we're sending. So for the red curve here, we are sending 5 data packets and then 3 equations. And now you see we have a perfectly flat curve, which scales nicely with the number when we increase the number of users. The penalty that we pay is up here when we have only a small amount of receivers, because sometimes we don't have any unlucky receivers. And this means that we are sending all of these extra equations for the benefit of no one. So they don't really, they're just overhead in the system at that point. If we take a look at the 10% packet loss case, we see a similar picture. At 100 receivers, we see the uncoded system. We now have to basically retransmit everything like 3.5 times. And again, we see a similar improvement by using the traditional small block FEC code. But the question is whether or not we can actually do better than this. And it turns out that if we use something like the RLNC code, it's actually possible to do even better. And this is what we've tried to simulate here. Remember, with the RLNC code, we can have all of the data packets within a single block, and we can produce as many equations as we want until all of the receivers are complete. And this means that now we don't have to, all the equations that we're sending describe the entire file, and this means that we just have to overcome the packet loss on the network. So the worst performance we will see is going to be dominated by the receiver that lost the most packets, basically, and we just have to overcome the network loss. And we see already the substantial improvement in efficiency here. If you look at the 1% network loss case with this approach, with the RLNC single block approach, you can see that at 1000 receivers, we only have to transmit every packet on average 1.05 times. So we have only a 5% overhead in total, which is a really significant improvement. And for a packet loss of 10% on the network, we also have a substantial improvement. And another thing which is really, really important to mention in this case is that this system works without feedback at all. This is fully stateless. There is no communication from the sender about which packets were lost back to, no communication from the receivers about which packets were lost back to the sender in order to get this type of performance, where in this case over here, we still need feedback in order to understand whether or not we need to retransmit more from a specific block, or whether or not in the uncoded case we need to retransmit any specific packet. So this really gives us superior performance even without any feedback in the system, which of course would also have a cost even if it was possible. So the theory here is really beautiful, right? We implementing OTAcast on top of a single block RLNC code definitely seems like the right approach in order to build this really, really efficient system. So let's see what happens when we try to implement this. So there are two things that are important, or at least two things that are at least important when we try to implement something, and that is one, the memory consumption of our algorithm, and second, the speed of our algorithm, or the coding throughput that we can get with our algorithm. So let's take a look at these two cases. So here we take as an example a single file of 250 megabytes, and we split this file into 1400 byte symbols or data packets, which could be sent over the network. And this means that we will end up with something like 180,000 symbols in our system of in our equation system. So we have 180,000 symbols in this data matrix M, and each of them would need to be multiplied with a coefficient, and we would create a sum of all of these and then send that out as an equation. And you can already imagine probably that even if the coding coefficients since we have to do Gaussian elimination, for example, at the receiver, storing the coding coefficients in the Gaussian elimination, if we use just a single bit for the coefficients, would result in a memory consumption of 4 gigabytes. If we used, for example, 1 byte for every coding coefficient, we would need to have 32 gigabytes of memory just for the coding coefficients in the decoding algorithm. So this is already out of scope for most types of devices, especially like smaller embedded devices or things like this would never be able to handle anything like this. And also, if we look at the throughput of the algorithm, it would be pretty horrible. So here we have some benchmarks from a standard RLNC algorithm where we slowly increase the number of symbols inside the block, basically. So in this case we have 16 symbols, and then we have a throughput which is pretty impressive, more than 80 gigabits per second on the encoder and more than 60 gigabits for the decoder. And then you can see as we increase the amount of input symbols, the throughput is slowly dropping off because the computational complexity is increasing and increasing as we do this. And already here with 1,000 symbols in a block, we have a throughput that is now hovering a little bit above 5 gigabits per second for the encoder and a little bit less than 5 gigabits per per second for the decoder. So in this case, when we have 180,000 symbols, the throughput of this would be horrible with a standard RLNC algorithm. So there's no way that we're going to be able to implement this by just having everything inside a standard Gaussian elimination decoder. That simply wouldn't work, both from a memory perspective but also from a throughput perspective. So the solution that people have come up with in order to deal with this problem is that we simply need to split this file into multiple smaller files or input blocks. So we could, for example, split this into 250 blocks of 1 megabyte and then divide that into symbols. And then we would be transmitting from one of these 250 blocks when we were sending to our receivers. The problem with that approach is that if we have all of these input blocks here and we have all of our receivers moving around here, when we have to pick one of these input blocks, which is essentially an encoder and a decoder. So when we pick, for example, block number 2 and transmit an equation from block number 2, we might have a situation, especially towards the end of the transmission, where a lot of the receivers have already decoded this particular block of the file, right? And it's only beneficial at a very small subset of the receivers. And this means that we are losing efficiency in the system. We are not getting, we're not benefiting all receivers when we do a transmission. And this is a problem for our solution. So we really want to find a system or a solution where we can have all of our data within a single block, such that when we transmit, it's with a very high probability always useful at all of the receivers. And this is where Perpetual RLNC comes in. So let's take a look at how Perpetual RLNC actually manages to solve this problem and put all of these symbols into a single block, such that we can have the most efficient solution for our OTAcast transmission. So there are a couple of key concepts in a Perpetual code. The first is that it is a concatenated code, and that is shown over here and what we mean by that. So basically imagine here you have all of your input symbols, they are up here, and you have 180,000 of them, for example, for the 250 megabyte file. For the 250 megabyte file. So the first thing we do is that we run these 180,000 symbols through what is called an outer encoder. And the outer encoder is going to produce some equations describing this input data and just interleave it with the original input data. So now we have our original input data plus some equations that are also describing the original input data created by this outer encoder here. And this is going to be the input for our inner encoder. And so the inner encoder is then producing the equations, linear combinations of these symbols here that we're going to be sending to the network. And I'm going to get back to why this is important a little bit later. The second concept in perpetual coding is that it's very, very sparse. This means that we are only going to be the equations that we are sending is only going to be a linear combination of a very small subset of the input symbols. But it's going to be locally very dense, which means that we will have a lot of zeros surrounding our non-zero coding coefficients, and then we're going to have a small group here of non-zero coding coefficients, for example. And this is a special structure that is created in the perpetual code such that we can maintain the sparsity during decoding. Because one of the traditional problems, or one of the problems that you have when you try to do something that is a sparse code, is that if you have two sparse vectors, let's say two vectors of 100 elements each, and there are two random non-zero elements in each vector, and you add them together, it's very, very likely that the output will have 4 non-zero elements in it, because otherwise the two non-zeros would have to exactly overlap, and that is unlikely with a randomly picked vector. So because the decoder is actually doing a lot of vector additions and stuff like this, it's very difficult to maintain the sparsity, which means that having a lot of zeros in the decoder can be difficult to maintain. And this is one of the things that the Perpetual code uses, this very sparse but locally dense structure to keep that property intact as the decoder operates on the data. So let's take a look at what it is that this inner encoder is doing, because this is what is preserving this sparsity in the structure. So the way that the inner encoder works is really simple. When we want to produce an equation, we have our input symbols here. There are 180,000 of them, plus these interleaved outer code symbols. And what we do is we simply pick an offset somewhere. And then we do a linear combination of the following width -1 symbols. So in this particular case, we have a width of 4. And then we pick this S2 as our offset. And then we do a linear combination of S2 plus S3, R0, and S4, which is the following 3 symbols. And this is then going to be the equation that we are sending out on the network. And in order to send a new equation, we just pick a new random offset somewhere inside these 180,000 symbols, and we do a linear combination again. And this process just continues and continues from the sender. And what is happening on the decoder side is that we are receiving equations that are just this linear combination of in total 4 symbols here, and they are just being inserted into this decoding matrix here. And if we look at what is actually happening when the reason why we can maintain the sparsity is what we are trying to illustrate here. So let's say that we have already some equations here. This C1 means that it's a combination of symbol 1, symbol 2, symbol 3, symbol 4. The yellow one here is a combination of symbol 2, symbol 3, symbol 4, symbol 5, and so forth down. The C2s here just means that they are not the same. The coefficients here are random, right? So it's not that it's the same coefficient. They are 2 randomly picked coefficients. It's just that they are linear combination. Both of them are a linear combination of the symbol 2. So let's see what happens when we receive a blue packet. And the blue packet also turns out that it's a linear combination of symbol 1, symbol 2, symbol 3, and symbol 4. So what we can do is because we already have the red equation here, we can actually eliminate this coefficient here by subtracting the red equation from the blue equation, and we get a 0 here, and now we're left with just something that is a linear combination of symbol 2, symbol 3, and symbol 4. And because we already have the yellow equation, which is also a linear combination of symbol 2, we can also subtract the yellow equation from the blue equation and create a new 0 here. But notice how we are also introducing a new non-zero coefficient here at the end. And now we have something that is a linear combination of symbol 3, symbol 4, and symbol 5. And then we take the green equation here, which is also a linear combination of symbol 3, and we subtract that from the blue equation, create a 0 here, and now we are introducing yet another non-zero at the end of this blue equation here. So now we end up with something that is a linear combination of symbol 4, symbol 5, and symbol 6, and this is actually one of our missing pieces here, so we can pop that to our decoding matrix, and we will have filled this gap here. We will have what we call a pivot for symbol 4. And but one of the things you see is that we can never increase the width of these equations. We can only decrease the width of these equations, which means that we can maintain the sparsity in the system, we can maintain the memory consumption, and the computational complexity can be kept sort of under control as we do this in the system. And one of the nice things is also that you'll notice how we can sort of, when we drop in a new equation, it will sort of trickle down through the matrix and find the empty spot or the place where we are still missing something. And sometimes we explain this by imagining that this is sort of a staircase where we are throwing balls down the stairs, and when they hit some place where we haven't yet received anything, they become a new step in the staircase. And we call this sort of the trickle effect. The equations sort of trickle down through the decoding matrix. So if we look at the decoding steps from the very beginning, we have 3 phases. The first phase is the insertion phase. Because the decoder hasn't received anything in the beginning, the initial phase is simply just inserting symbols into their corresponding location. So because it's almost empty, we just insert the equations. There's a low probability of them hitting a spot that has already been taken, so we don't really have to do any work in this phase. And this accounts for approximately 63% of the work that we're doing in total. The second phase is this trickle phase. In this phase we don't have a lot of gaps left, so we are starting to hit spots where we already have a pivot in place, and the equations start to trickle down through the decoding matrix. And this goes on until we reach approximately 98% of decoding completed. And at this point, the trickling starts to be computationally expensive. So finding the empty gaps means that the equations have to trickle very far, and this is becoming computationally expensive. So what we're doing there is that this is the place where we are activating our outer code. Remember that some of these symbols are not actually data symbols. They are themselves a linear combination of data symbols. And this means that when we are at the very end with like 98% of all the pivots found, we can activate these outer code symbols, and they will be used to close the remaining gaps that we have. And so we basically take them out and we sort of reintroduce them into the decoding matrix, and they will fall into the spot where we still have gaps, and decoding will complete. So let's take a look at the efficiency of this system. So remember, before we had a 250 megabyte file and we chopped it up into 1400 byte symbols, which gave us this 180,000 symbols in total. With Perpetual and a width of 32, which means that every equation that we're sending is a linear combination of only 32 out of these 180,000 symbols, we have reduced the memory consumption of the decoder to approximately 700 kilobytes if every coefficient is a bit, which is what we normally use. And this is indeed feasible to do even on embedded devices like a Raspberry Pi or similar. And also the throughput of the algorithm is kept at a reasonable level. If we take this Raspberry Pi here, which has a 1.4 gigahertz CPU, we can see that we can actually do, for a 250 megabyte file, we can sustain an encoding throughput of 144 megabits, and the decoder is still running 77 megabits in speed. And this is really interesting because just this 250 megabyte file is not possible to do with any other erasure correcting algorithm that we know of. Most other erasure correcting algorithms would have a maximum block size of approximately 70 megabytes, and here on a simple Raspberry Pi we are exceeding that by a substantial amount, and we can go up even to a gigabyte in size, in file size, and still maintain a reasonable performance. The algorithms are really stable, depending, even given much larger inputs. And on the more beefy i7 machine, we can maintain more than a gigabit, almost 2 gigabits of throughput on the encoder and decoder. So there we are also performing really well. So this really gives us the performance that we want in building a fully stateless system that doesn't require any feedback from the receivers. So in summary, what we have with the OTAcast solution based on the Perpetual code is a solution where we have fully stateless communication, which means that we have on-the-fly joining. So devices can come in and out of range of the sender seamlessly. We have blind sending, which means that the sender can send without having any feedback or communication to the receivers and do it in a super efficient way. Of course, in many practical systems, you may want some form of feedback, at least when the transmission is done and things like this, but there is no requirement in OTAcast to have any feedback. It also inherently supports multi-sourcing, so we can have two encoders transmitting the same file seamlessly. We can have multipath, which means that you can transmit over multiple different networks simultaneously, like Wi-Fi, cellular, or satellite, and combine these transmissions at a receiver seamlessly as well. One of the other nice things is that OTAcast is just a software library. We built it as a C++ library, which means that it can be integrated into almost any system where C++ can be compiled. We have a Python module which is available for playing around with the algorithm, doing proof of concept, for example. And we also have a standalone application that you can run on a computer, on a local network, for example, just to try out the algorithms and the functionality. There's a couple of references if you want to dive really into the theory behind Perpetual codes. The first one is Perpetual Codes, Cache-Friendly Coding by Peter Majunmunkov from MIT, formerly from MIT. And the second one is a Perpetual Code for Network Coding by Janus Heide. You can find those papers on Google, freely available if you're interested. And if you want to learn more about OTAcast and the use cases, feel free to also visit steinwurf.com/OTAcast, where we have some more information available, and also feel free to reach out if you have questions or are interested in OTAcast for your own projects or product. So thank you very much for listening.